Hello and welcome everyone to the next event in our webinar series, a presentation by Reza Salem, Associate Director, Thorlabs Laser Division, and Kevin Lascala, Director of Engineering, Thorlabs Quantum Electronics. My name is Ning, and I will be moderating today's talk. Reza Salem holds a PhD in electrical engineering from the University of Maryland and worked as postdoctoral researcher at Cornell University. Prior to joining Thorlabs, Dr. Salem co-founded Piclus LLC in strategic partnership with Thorlabs. Kevin Lascala holds a master's in electrical engineering from UC Berkeley and has been developing quantum cascade and interband cascade lasers since 2007. Throughout this talk, please feel free to submit any questions you have using the Q&A tool. Reza and Kevin will be answering any questions at the end. Now I'd like to hand the talk off to Reza.
Hi everyone, my name is Reza Salem and I'll be working today with my colleague Kevin Lascala to talk about our work on dual comb QCL Spectrometer and introducing our product and highlighting some of its advantages, particularly when it comes to performing high time resolution spectroscopy experiments. So just to show a little bit of outline of what we're going to be talking about today, first we start by discussing infrared spectroscopy techniques in general, starting from the conventional approach with FTIR systems, then moving into dual comb spectroscopy approach and talking about pros and cons of different ways of measuring the absorption of spectrum in the infrared. And then we talk a little bit more specifically about our product, Iris F1 spectrometer, the specifications, features, and benefits. And I also offer a very brief application example towards the end to show you some of the capabilities of the system. Then in the last segment of the talk, I hand it off to my colleague Kevin, who will be talking about a specific application we've been exploring on air quality monitoring in a joint effort with Professor Wysocki and a few other Princeton University professors, and specifically talking about some applications on that front with landfill monitoring. So to start things off, looking at infrared spectroscopy, this is a decades-old technique for measuring chemicals and identifying and characterizing different compounds. And the staple in the industry has been the Fourier transform infrared spectroscopy system, or FTIR, which was invented in the 1940s. So this is really a technology that has matured. You can find it in all chemistry labs. You can find it in various industries, from pharmaceutical to food and drink manufacturing. And it's really based around a very simple concept. It involves two important elements. One is a broadband light source, which typically is a black body source. We'll talk about that a little bit more in the next few slides. And that light source is coupled into an interferometer, which consists of a stationary mirror and a moving mirror. So by moving the mirror, essentially one can scan the interferometer and create what's called an interferogram of the light source in time domain. And that interferogram then is Fourier transformed and converted to spectrum. So with this tool, a sample absorption spectrum can be measured by essentially placing it on the beam path, and then it can be analyzed to determine what the sample is. So this technique comes with some pros and cons. The biggest advantage of FTIR systems is their broad spectral coverage. So these thermal sources that are essentially lamps or glow bars, they're all black body radiation sources. They offer a very broad spectral coverage. In fact, you can find a few of them in turnkey systems on the Thorlabs catalog. For example, I've shown the SLS 303 here with a spectrum that essentially covers from visible all the way into far infrared. So the entire region of interest can be covered in one light source. But FTIRs have their own disadvantages, and the drawbacks, I've split them into two categories. One I call practical drawback, which is the limited brightness of these thermal sources. Because these sources are spatially incoherent, the beam quality of these sources is very poor. compared to a laser system. For an example, I've shown at the top of the slide right here, where my pointer is, I'm showing the beam profile from one of our own black body emitters after collimation. So even after collimation, you're essentially seeing an image of the filament inside the black body source. And this essentially translates to a very poor beam quality, which limits some applications. It works for some, but it limits some certain other applications. One example is when light needs to go through an opaque sample, so the limited brightness becomes a limiting factor. Another one is for long distance propagation. For example, in a gas cell like this, you're talking about tens of meters, maybe 100 meters of beam propagation, which becomes very difficult to do with an incoherent source. And similarly, in microscopy applications where you're looking at a very small spot, so you want very high spatial resolution, this also becomes a limiting factor. I should also add that this limitation has been addressed in the last few years by the emergence of new technologies and broadband supercontinuum lasers. In fact, Thorlabs recently released a long-wave infrared supercontinuum laser that offers essentially orders of magnitude more brightness and a very good beam quality in the infrared region. But the actual fundamental drawback of FTIR is something that is much harder to overcome, and that comes from the design of the system. If you remember when I talked about the concept, there is a moving mirror in the system that this mirror essentially goes back and forth and is scanned usually at Hertz level or lower in all the commercial systems that are out there. So this limits the temporal resolution of the measurement to, at best, hundreds of milliseconds. So this really makes it limiting for mapping out transient effects, single shot measurements, things of that nature. Now, the concept that we want to look at today as a way to overcome that fundamental limit is dual cone spectroscopy. It's a technique that was invented years ago, probably a little more than a decade ago, and it's been adopted in various different settings, for example, frequency metrology. In the spectroscopy area, the way we apply it is the following. So you have a frequency comb replacing the broadband source. A comb is essentially a spectrum made of discrete and regularly spaced spectral lines. So that's where my cursor is right now. You see a bunch of lines equally spaced in the optical frequency domain, and that's called a frequency comb. Now imagine if we take two of those, and not only we take two frequency combs, but we also take them at slightly different mode spacings. So the mode spacing between the comb teeth in the first comb is, let's call it FREP, and in the second one is FREP plus delta FREP. So there's a small difference between the two. What's going to happen is that if these two optical frequency combs go inside of a detector together and they beat together, what will happen is that a frequency comb in the RF spectral domain is generated coming out of the photodetector. And what's important is that the frequency comb in the RF is going to mimic the properties of the two frequency combs in the optical domain. Now, imagine if one of those frequency combs was going through a sample and had some molecular properties in the spectral domain imprinted onto the comb, as shown here. These frequency features can directly translate and transfer to the RF frequency comb. So essentially, by measuring the RF frequency comb, one can determine the absorption spectrum of the sample. So that's the concept, and kind of looking at some of the fundamental parameters here. As I mentioned, we have what's called a local oscillator, so one comb that just goes through, and a second comb that goes through sample absorption. So that's the signal shown with orange here. And they come at two different repetition rates with a slight difference, delta FREP. As they go through this detection, the comb teeth in the RF domain, it can be shown mathematically that they're going to be separated by delta FREP in the frequency domain. So what that means is that to resolve this comb after processing, the acquisition time to resolve it could be as short as 1 over delta FREP. This is a really key parameter, and we come back to this in a little bit later when we talk more specifically about quantum cascade lasers, that in the case of quantum cascade lasers, this delta FREP is large enough that the acquisition times could be as short as a microsecond. And that's really the key here without any moving parts, you could capture the spectrum in a microsecond. Now, before we segue into that, let's talk a little bit about quantum cascade laser frequency combs and what we mean by that. Quantum cascade laser is a technology that offers high power laser emission in the key region of mid-infrared. And mid-infrared from 4.5 to 12 micron is actually a really important spectral region for a lot of molecular fingerprinting experiments. So a lot of chemicals have key distinguishing absorption features in that region that can be used to detect them. Thorlabs has vertically integrated QCL manufacturing capabilities, and it starts from material growth and gain spectrum design to chip level design, characterization, high volume manufacturing, and also to laser package design and assembly. As shown here, this is an example of a laser package after the chip has been packaged in a housing with a collimated output beam. And then we also have capabilities to put these laser devices in an actual system platform with a turnkey offering, with electronics and everything you would need to operate it. And what's important about these QCL devices is that just like most other single mode laser systems, they have a very nice single mode output beam quality, as shown here for one of our products. So this goes back to the brightness considerations that I mentioned with lasers. Now, QCL combs are a little different from standard combs, and they were actually invented in around 2012 in this Nature paper that I've referenced here by some of the founders of FTIR Sweep, the company that we'll talk about a little bit more, that Thorlabs acquired the technology from. This is an example of a quantum cascade laser frequency comb in the optical domain. So you can actually see that we have roughly 200 lines. They are pretty densely spaced. So in the frequency domain, they're about 0.3 wave numbers or 10 gigahertz apart. And you're getting about 200 lines, so that covers more than 60 wave numbers of spectrum. So this is, in many cases, enough to map out absorption spectra from solids and liquid samples. And this technology really is designed around two important design factors. One is designing gain spectra that are very broad. So there's a lot of material design considerations that Thorlabs has also developed and owns, and also some waveguide dispersion engineering to achieve the comb operation. And just finally to mention, there are some dead zones you might have noticed inside of that spectrum. Just want to point out that these are actually water absorption lines in the measurement system. So it actually is another way to show that the system can be used for absorption spectroscopy. Now going back to our parameter space with the optical and RF domain and the acquisition time of 1 over delta F rep, and look at the specifics of QCLs. In QCLs, the repetition rate of the comb in the optical domain is about 10 gigahertz, as I mentioned, or 0.3 wave numbers. And the difference between the F rep of the two combs ends up being about a few megahertz. So inverse of that few megahertz gives you microsecond. So that's why these measurements can actually be performed in such fast timescales. Now, with that background, I want to talk a little bit about the product that we are now offering through Thorlabs. So technology for Iris F1 spectrometer, which is the product we're highlighting here, was initially developed and commercialized by FTIR Sweep in Switzerland, a company that was started from ETH Zurich in Switzerland. And this technology was transferred to Thorlabs last year. And currently Thorlabs is manufacturing and delivering the system to customers. The system is, as shown here, is developed in a tabletop platform, is designed for maximum flexibility. For example, you could switch out the QCL dual comb module that goes in the system so that you can cover different bands, because each QCL covers about 60 wave numbers, as I mentioned. Now, by switching different QCL modules, you could cover different bands of the spectrum, and the system allows it to do that in a very seamless and easy way. It also comes with sample compartment for processing the sample within the spectrometer, and also all the detection that is required to do the measurement. Just at a high level in terms of specs, we have a time resolution down to a microsecond, as I talked about in detail. The wavelengths we're covering range from 5.6 to 11 micron at the moment. The spectral coverage for one dual comb source is about 60 wave numbers. And the spectral resolution determined by the spacing between the comb teeth is anywhere between a quarter wave number to half wave number. So that's 8 to 15 gigahertz. It is possible to operate the system in what's called a high resolution mode by essentially sweeping the comb lines. And this could actually yield resolutions that are unprecedented, down to 10 megahertz. And this is something that we won't talk about in detail today just because we don't have enough time, but is a feature that exists with the system. So just to summarize some of the key features and benefits of Iris F1 spectrometer, one is the high speed. We talked about that, about a microsecond resolution. You can map out fast processes, and we'll talk about this in our application example in a minute. The second one is the high brightness. These are laser sources, so single mode laser beam comes out of the system, which allows measuring optically thick samples, which one would call real life samples in many cases, so that you don't have to come up with very thin samples to be able to get the light through. Compared to other laser spectroscopy systems that are very narrow band, for example, using a DFB, this system offers multiple wavelengths at the same time. So although it's not as broad as an FTIR light source, it is still much broader than most laser systems. So it offers 60 wave numbers, 200 lines. So this allows to map out fairly complex mixtures and processes and multi-species samples detection. And finally, I'm only touching on this, but we could certainly provide more information for anyone who's interested. There is a high resolution way to operate the system to get down to 10 megahertz spectral resolution. And this could be useful, for example, in gas spectroscopy. Now to zoom in on one specific application, but very briefly, this is an application that was actually demonstrated by the IR Sweep founders a few years ago. One of the first demonstrations that they did, and they did many different demonstrations of different processes over the years. But I picked this because it had some interesting aspects that kind of ties in with what we talked about today with time resolution. So in this study, they're looking at kinetic analysis of irreversible protein reactions that are essentially time resolved and measured in single shot to be able to map out processes that cannot occur again. And the concept was demonstrated in a photoactivated bacterial rhodopsin material. And just to put a little more details here, these molecules, these proteins, essentially go through different states after they're photoactivated, let's say with a YAG laser that shoots a pulse at the material. But the processes happen at different time scales. There are processes that happen in microsecond and some that happen in millisecond lifetime. But what's key is that these different processes have slightly different infrared absorption spectra. So as shown here, processes that happen between 0 and 12 microsecond are slightly different in absorption compared to processes that happen in 4 to 4.6 millisecond, for example. So by time resolving the data, you could actually see different states of the material moving through the process. Now, this can be done with what's called a step scan FTIR. This is a special mode of operating an FTIR where you would move the mirror position hundreds of times, in this case 450 times, and at each point you do multiple averaging to get a good signal to noise ratio. So essentially, you could end up with 20,000 repetitions to be able to map out a process like this. Now, the problem with that, not only the fact that this cannot be measuring anything that's single shot, but also repetitive measurements really require, in many cases with biological samples, require prohibitive amounts of sample. So sometimes you cannot have enough sample to be able to repeat this measurement 20,000 times. So that was the focus of this study. And what they demonstrated was that in comparison with the step scan 20,000 repetitions, they could do the same measurement and essentially produce the same results that the step scan FTIR produces with only 500 repetitions, which is far fewer, and still get reasonable signal to noise ratio to be able to distinguish between different states of the matter in different time scales. And what's also interesting is that the signal strength that they ended up with at far fewer repetition was still stronger, and this is really attributed to the high beam quality of the laser. And finally, before I conclude, this paper also included a single shot measurement. So now instead of 500 measurements, you could actually discern the information from one shot measurement. It's obviously not as good of a signal to noise ratio as repetitive measurements because the averaging is in there, but it does provide enough information to be able to decouple these different states, which is a really unprecedented and unique feature that the Iris F1 spectrometer could offer here compared to, let's say, an existing FTIR technology. So with that, I'm going to hand it off to my colleague Kevin to give you guys a little bit more detail on one of the applications that we're also exploring right now.
Thank you, Reza. So what I want to talk about now is where we've been exploring other applications for this technology that also might allow us to get out of the laboratory and find some real field applications. So in order to do that, we should go back and talk again about some of the advantages of dual comb spectroscopy. So as Reza just pointed out, the beam is very bright, both spectrally and spatially. This allows high sensitivity measurements. It's an optical technique. So we can actually measure things remotely. Many of the different techniques that you might see require local access to a sample. We could measure something at a distance potentially because we're sending a light beam out. The sources that are used in the dual comb spectrometers have broad spectral coverage, so we can see multiple chemical species and measure them simultaneously. And finally, we can make rapid measurements. As Reza just pointed out, we can take single shot measurements that encompass the entire spectrum. We can do that very quickly. Obviously, we have a lowered sensitivity when we do that, but sometimes that's good enough to try and accomplish our goals. We can also monitor dynamic processes. That was illustrated as well in the last example. Finally, there's no moving parts. This makes the technique potentially suitable for deployment in a field, in a mobile environment, in various weather conditions, environmental conditions, and so forth. So what we found is that emissions and air quality monitoring really play to dual comb spectroscopy strengths. You see that that many of the advantages are required for this type of application. We want to make high sensitivity measurements. We want to measure things remotely. We want to measure multiple chemical species simultaneously, and we want to do this quickly so that we can potentially scan a large area when we're performing air quality monitoring. So to explore this further, we put together a team, and this team started with our collaboration with Professor Gerard Wysocki at Princeton, with whom we've been working for several years. Back to, I think, 2017, we started working with Princeton. And he's really been an expert, along with the group at IR Sweep, on QCL dual comb spectroscopy. We added some other team members, though, to really explore this, including Elie Bouzed, who's a fluid dynamicist, Mark Zonlo, an atmospheric chemist, Jaime Fisak, who's a roboticist, and we brought back Link Patrick, which is one of Gerard's former grad students, as a project manager, and Reza and I are in the team as well. So as part of the NSF Convergence Accelerator program, we proposed that we would use dual comb spectroscopy to explore environmental sensing. Along the way, we added some other team members, so I'll introduce them now. This is the team from SCS engineers who are experts in waste management, landfill monitoring, and various chemical techniques to monitor and landfill emissions and really propose ways to mitigate those. So how did we get? I've already previewed. Reza's already previewed. How do we get to landfill? So the concept we came up with to perform environmental monitoring is this: we have the dual comb system on a mobile platform, and then we send the beam out to a robotic drone. That drone would have a retroreflector mounted on it, so that would send the beam back to the dual comb system for analysis. In between, you'll have some sort of emission happening and a plume developing, and you see illustrated here. So by moving the drone around, we can scan that plume and then perform some inverse modeling to figure out the location of the emission. We can see the concentrations, the the concentration is a function of position, and localize the source as well. So who might find this useful? Potentially first responders. And in the case of a chemical spill, it's very important to understand what chemical you have, and where it is. Where is the plume going? You don't want to just base it completely on the wind direction, so that you don't send first responders into a hazardous area. Industrial emissions, where you have some sort of factory facility that is producing emissions. What are the concentrations and where are they going? Agricultural and farming. What are the emissions, but also what's the local environment? So how does that affect agriculture? You can also monitor the health of the plants. Landfills and wastewater facilities, basically monitoring how we treat our waste and how that affects our local environment. Oil, gas, and petroleum. So when we're doing oil refining, how much methane might be emitted, how many other chemical species. There's some hazardous species that could get emitted there. So part of what we did during this project is poll a number of different experts in the field and find out what the state of the art was and what the needs are. And many of the techniques are really either very expensive, they have limited resolution, things like flying a plane over emitting source, that's quite expensive and difficult. Using a satellite can only show some sort of column integrated information, so you're looking down from space. You can't see any sort of vertical information as to how the plume is developed. And generally things have low resolution. We also found that actually there's a lot of landfills out there, and they have an effect on the local environment. You can have situations where these landfills release methane. They're currently monitored for that, but there's also other chemical species that can be emitted. And some of those species both bother the local neighbors in terms of odors that are emitted, but some of them are actually hazardous, and some of them indicated that there are problems underlying with the landfill that need to be addressed. And we'll talk about that in a few slides. So landfill monitoring is the one we selected, where we thought we really could have a real impact by upgrading the existing technologies and techniques that they're using. So what is the problem? The problem is the landfills need to be monitoring. The EPA currently requires that landfills are monitored for methane emissions. When people are doing that, they have to send people out. It's as you can see, there's pain points. It's labor intensive. You can see the picture here of the landfill. You've got people who are walking over this potentially unstable environment. It can be hard to find the leak. You have to sample at very high rates to really localize the leak, which means more passes, more money, more time spent on the landfill. You want to quantify it to find out, is it above or below a critical threshold, and know how it affects the environment. Want to understand if something's emitted, how it disperses. So how does it affect the neighbors and the local area? And then you don't want to get mixed up and think that you're measuring one chemical species and not measure that correctly. So how are we going to address all of these pain points? The first two, we have a drone. So we don't have to have anybody walking the landfill anymore. The drone can fly over the landfill. There's no danger. There's no person involved. We just need a clear line of sight over the landfill. The autonomy plays a role in that we don't have to get the people too close because we've got this autonomous drone. Now, by using the information we can collect from the dual comb system combined with the drone, we can then model the plume and perform what's called an inverse model to try and localize the leak and quantify the amount of chemical that is actually being emitted from the landfill. Finally, because we have a detailed spectral measurement and we have broad spectral coverage, we can differentiate between different chemical species that may be emitted. So we really think the dual comb system has a lot of potential to really add to what's being done already at landfills and really help the landfill operators themselves understand what's going on and really do a service for the neighbors of the landfill. So, is this a real thing? Yes, it is. A quick Google search will reveal to you that there are existing problems with certain landfills. One of the ones that have made the news lately is the Chiquita Canyon landfill, and that there's tens of millions of dollars being spent on this landfill to mitigate the burning that's happening underneath the landfill, and that if this type of situation can be identified early and mitigated early, you won't get to this situation where, as you can see, you add those numbers up, it's over $130 million that's being spent to address this. So some monitoring really could kind of cut this problem off the pass and prevent not only the mitigation, but all the lawsuits and all the back and forth with the EPA and the danger to the community in the meantime. That's not the only one, though. So there are thousands of landfills in the U.S. Depends on the size and how you rate them, but at least 5,000. The complaints can happen. We hear odor complaints about the Sunshine Canyon landfill and how they've been increasing over time. And you're getting hundreds and hundreds of complaints, even hundreds a month, from the local community about that particular landfill. So if you could monitor for these things before that people can detect the problems with essentially through smell, then they can avoid the consequences of this and really help keep the community safe. Here we have legal settlements that a landfill has made with the local community, and so on and so forth. So why are we going to be able to do this? Why do we hope that we're going to be successful? So the advantage of dual column spectroscopy, to now get a little bit into technical detail, there's many different chemical species that we would like to monitor in this environment. You can see that you've got benzene, hydrogen sulfide, methane, dimethyl sulfide, and so forth. Well, what we've done is plotted the absorbance for those chemical species over a range that can be covered with one of our dual column systems. This one's around 8 microns. So we see that although there's a lot of structure here, that, for example, the green trace is the butadiene, and that has kind of a smoothly varying structure over the range, where you see a completely different shape to the formaldehyde trace. Look at ammonia. We can go through the whole list, but the point is that there are distinct spectral features over the same range. Now, that might not be very convincing because there's a lot of peaks. Could you actually differentiate them? But when we went through the analysis, we put together what's called a confusion matrix. And what this matrix shows is where you've got sort of the brighter colors, you see, well, if we try and perform some calculations on taking various measurements and how well these spectral overlap and where they have common features, and basically we're taking the dot product of two spectra, what kind of correlation do we have between those two? And you see that the colors are fairly light. So we've got low correlation coefficients. So a correlation coefficient of either 1, which would be bright red, or -1, which would be dark blue, would mean that the two chemical species are either correlated or anticorrelated. In this range, all of them are actually quite low. So all of them are below 0.2, 0.3, that type of measurement, which means that they're not very well correlated, which means we can actually distinguish them. So you start to look over in the side, and we're getting down to ppm level sensitivities for these type of measurements, which is really good and generally where we need to be to perform this monitoring. And so when you look at these chemicals, it's really a great technology for doing this, as pointed out by one of the engineers that we're working with in the landfill area. None of the existing tools to assess emissions actually pull this off. The existing technologies generally involve walking through the landfill with some sort of, it could be a flame ionization detector, it could be a tunable diode laser that only can measure methane, but they can't really say, was there any hydrogen sulfide there? Was there any benzene there? We can do that with this technique, and we can do it over the whole landfill and do it in a much safer way. So we're really excited about this. This is something that we've submitted to NSF for phase 2 funding. So we hope that we'll have the opportunity to work on this in the future with the Princeton team. So with that, I'd like to thank you and hand it back to Ning.
Thank you, Reza and Kevin, for that informative presentation. We already have a few questions. Again, I'd like to invite you to submit your questions this time. So our first question, the QCLs have broad spectrum, but are they locked to stabilize each comb? Is that necessary with this technique? Or as long as FREP and the delta FREP vary the same, it's safe?
Yeah, good question. So in this case, the QCL combs are not like some of the more conventional stabilized combs that you find in frequency metrology, such as fiber combs or ultrafast laser combs. But in this comb operating regime, they're stable enough that with the right type of processing or post-processing of the data, the FREP and the FCEO, the two parameters that essentially determine where the comb is, can be extracted from the data. So actually, a lot of the novelty and the know-how in the IRIS-F1 spectrometer that was developed circles around that algorithm that essentially traces those parameters of the comb by post-processing the data. So they're not stabilized, but they are in a phase lock state as a comb, such that this type of post-processing is actually possible.
Okay, thank you, Reza. Our next question. What is the wavelength, wave number accuracy of the system, and how is it calibrated?
Yep, so this, I would say, depends on the specific application. The calibration can be essentially adapted to what's needed. The system does not come with a known reference calibration wavelength, but the comb lines are at a given current and temperature, they're stable. Therefore, depending on what kind of calibration you would use to actually determine the wavelength axis in the system, you could determine the accuracy. Every system that gets shipped typically goes through a calibration with height trend data for a known gas, because regardless of where you are in the optical spectrum, in the mid-IR, you can find some known gases that you could calibrate the system to. So at that level, it can be guaranteed to have enough accuracy to be able to correlate with the height trend data for a specific gas. For example, water would be the easiest one, but there are other gases as well. So that ends up being, limited in terms of accuracy to the width of those features, which would be somewhere in the sub-gigahertz range. So down to that level is easy to do. If more than that is needed, a different technique to do the final calibration can be adopted, for example, with a stable source or a cavity, which is not a standard, but can be discussed depending on the application. In reality, most of the applications that involve detecting liquids and solids, they have broad enough spectra that the accuracy that we currently offer with what I described in the calibration process is enough. But more than that can be done depending on what the user actually needs.
Thank you, Reza. So next question. What are the limiting parameters of the difference delta FREP between two combs? In other words, how can we increase the time resolution? And is there any benefit to doing so?
Yeah, that's a great question. So there are some trade-offs here. You could certainly design your QCL chips with slightly different length to end up with a larger delta FREP. And in principle, get higher resolution. The problem at some point is that to fill up that RF spectrum with 200 lines, if the spacing between them was, let's say, 10 times larger than what we currently have, you would actually need 10 times more detection bandwidth and digitization bandwidth and processing bandwidth to process the data. So at some point that becomes a limiting factor in terms of, how quickly you could process the data, or you have to compromise on the number of lines, which would be the spectral coverage essentially in the optical domain. So there are definitely some trade-offs there that are very interesting. What I would say is that in most practical applications, if you're looking at time resolutions down to, let's say, a picosecond or a femtosecond, there are pump probe techniques out there that can be used. And if you want something that is in the microsecond to millisecond, that's where I think there is a real gap in terms of technology that's available for spectroscopy, and that's where the system comes into play. So I think the microsecond to millisecond is really where we need to operate anyway with this instrument, and that's currently what the technology does.
Hey, Reza, I have a few more questions here. Can you extract phase information from a sample using this technique?
Yes, you could. That was something that I didn't have a chance to really do a deep dive into. So essentially, the system can be operated in two modes. One is called the amplitude sensitive, and one is called the phase sensitive. Typically, amplitude sensitive is sufficient and is simpler for operating a simple absorption spectrum measurement on a material that we're trying to detect, such as the examples that we showed. But in some cases, if the phase information is important, then a phase-sensitive configuration of the system can be offered, and that could actually extract the phase information of the absorption feature as well.
Thank you. One question. Can you still use ATR for weakly absorbing species?
Yeah, absolutely. These are, as I mentioned, we have a good beam quality in this case that you could couple into an ATR setup very easily and couple back into the system. We don't currently offer an ATR plugin, but it can easily the beam out of the laser system can be easily coupled into an ATR and then coupled back. And in fact, even fiber-based ATR systems were demonstrated by IR sweep at some point in time. So even that has been shown that it's possible. So there's a lot of possibilities that can be added essentially to the base system by coupling the beam out and coupling it back in.
I have one more question here. What are the typical power levels out of the system? What wavelengths are available?
Yeah, so power levels out of the system, actually powers that are achievable out of the QCLs are in hundreds of milliwatt, but typically the system does some attenuation on purpose to actually bring the beam power down to the level that can be easily detected without saturation on detectors, and also to reduce back reflection into the lasers. What's available in most of these QCL modules is in tens of milliwatts, let's say around 50 milliwatts is the maximum. And in terms of wavelengths that are available, we currently have 5 or 6 bands that are available within the range from 1,200 wave numbers or 1,000 wave numbers all the way down to 1,800 wave numbers. So different pockets of wavelength that are available. But we're constantly working on developing more and more QCL designs. As I mentioned, we have our own design capability. So this allows us to actually develop material and grow material to cover more of the band that's desirable for the infrared spectroscopy community.
That's all the questions we have. I believe that is all the time we have for today. I'd like to thank Reza and Kevin again for their presentation. Our next webinar will be on February 12th, presented by guest speaker Wim Bogerts, professor at Ghent University IMEC, Professor Bogus will introduce different classes of programmable photonic circuits, discuss the state of programmable photonics today, and illustrate this with recent demonstrations. You can register for this webinar by clicking the Register Now button below or on our website at www.thorlabs.com/webinars. Thank you very much for your attendance, and we hope to see you again.